Mount Kīlauea isn't slipping back into silence. It's accelerating, and the alarms are real. In October 2025, ground sensors revealed relentless inflation beneath Halemaumau crater, while micro-tremor swarms set off warning systems across Hawaii. Scientists track the mounting pressure, hinting at magma on the move, but the path it's taking might rewrite what we know about volcanic danger. The threat is unfolding right now, and what lies beneath could change everything. Why isn't Kīlauea stopping? And what happens if the mountain's heart beats too fast? At the summit of Kīlauea, instruments never sleep. The Uekahuna tilt meter, perched on the rim above Halemaumau, has tracked a steady climb. Over 10 microradians of tilt increase since mid-2025. That number, invisible to the naked eye, means the ground itself is swelling, pushed upward by magma accumulating below. GPS receivers anchored in bedrock confirm the movement, logging a persistent outward drift around the crater and along the southwest rift zone. The summit GPS station, coded KGPS, has shifted several centimeters since the last eruptive episode. These changes aren't random. Each uptick in tilt or GPS displacement plots a curve on the scientists' screens, a living graph of the volcano's internal pressure. The pattern is unmistakable. After each eruption, the ground deflates, then rebounds as magma returns. But in recent months, the inflation hasn't stopped. The current rise is sharper and broader than the cycles recorded before the 2018 disaster. Not just the summit, but the entire southwest sector is showing uplift. When plotted, the data form a rolling wave, with the highest crest centered over Halemaumau and a long slope trailing down the rift. This isn't just a curiosity for volcanologists. The tilt meters measure the volcano's pulse in real time, registering even tiny shifts in the earth. Each microradian a sign of mounting stress. GPS baselines stretching from the summit to the rift reveal the direction and speed of ground movement, allowing scientists to estimate how much magma is accumulating and where the pressure is greatest. For those who know how to read them, these plots are an early warning system. A sudden spike in tilt or a sharp jump in GPS displacement can precede an eruption by hours or days. The numbers now suggest that Kīlauea's magma chamber is not only refilling, but doing so at a pace and scale that hasn't been seen in years. The mountain is swelling, and the data leave little doubt something is building beneath the surface. Alarms pierced the quiet of the Hawaiian Volcano Observatory in the early hours of October 17th. For 36 hours straight, a swarm of micro-tremors rattled the ground beneath Kīlauea's summit. The seismic log showed hundreds of tiny quakes, some so faint they barely registered, others sharp enough to trip the network's automatic warning systems. The frequency of these tremors jumped without warning, clustering in bursts that scientists likened to the beating of a heart. Each pulse arrived faster and stronger than the last, echoing through the rock at intervals that seemed almost rhythmic. In the control room, every spike on the live seismographs brought a new layer of tension. Technicians watched as the tremor count rose from a handful per hour to dozens, then surged into the hundreds. The pattern defied the usual background noise of the volcano. These weren't aftershocks or the regular shudder of magma moving through old cracks. Instead, the data suggested something deeper, an organized migration, as if magma was carving a fresh path far below the surface. One volcanologist, staring at the screen, described it as a heartbeat under Hawaii. The analogy stuck. The entire mountain seemed to be pulsing, sending out a warning that was both mechanical and strangely alive. Audio recordings from the seismic array captured the low, throbbing hum of the earth in motion, a sound that, to those who know what to listen for, signals unrest brewing in the dark. By the end of the swarm, over 1,200 microquakes had been logged. The largest, still minor by earthquake standards, was enough to rattle lab shelves and prompt a flurry of text alerts to field teams. The tremors faded almost as quickly as they arrived, but the memory of that relentless rhythm lingered. For scientists, the message was clear. The mountain's pulse was quickening, and the source of that energy was still hidden somewhere beneath the ground. The surface data told only part of the story. The real movement was happening out of sight, deep below the summit, where magma and rock were locked in a silent struggle. Beneath Kīlauea's restless summit, scientists have spent years chasing shadows, hints of a hidden world where magma travels out of sight. Now, with advances in seismic tomography and ground deformation mapping, that world is taking on sharper contours. By sending waves of energy through the Earth and measuring how they slow down or bend, researchers have traced a broad dike-like corridor stretching from the heart of Halemaumau to the southwest rift zone. This low-velocity zone, mapped at depths between 2 and 5 kilometers, acts as a molten artery, linking the volcano's main reservoir to distant vents near Mauna Ulu and Pu'u'o'o. The evidence stacks up across disciplines. Earthquake swarms, clustered at 3 to 4 kilometers deep, line up along the corridor's path, each tremor a pinprick marking the magma's advance. INSAR radar overlays capture the ground's response, subtle pulses of uplift and outward movement that ripple along the rift, synchronized with the timing of these seismic flurries. Every inflation episode leaves a signature, a slow, outward bulge above the buried pathway, recorded in millimeters by GPS and tilt meters. Magnetotelluric and electromagnetic surveys add another layer. High conductivity zones, detected by sensors deployed along the rift, match the low-velocity regions seen in seismic models. These findings point to a continuous channel of partially molten rock, a structure that is both a product of Kīlauea's unique geology and a key to its unpredictable behavior. The lateral migration of magma isn't just theory, it's measured, tracked, and mapped in 3 dimensions. Rates of movement are slow but relentless. Modeling suggests magma creeps along this corridor at 1 to 2 centimeters per month, modulated by the pressure cycles that drive each eruptive episode. The pathway itself spans more than 10 kilometers, a buried bridge between the summit and the rift's outer flanks. As each new episode charges the system, the conduit flexes and swells, its shape revealed in the shifting lines of ground deformation and the echo of distant quakes. For the scientists at the Hawaiian Volcano Observatory, these images are more than academic. They are the blueprint of a living system, a guide to where pressure may build next, and a warning that the mountain's energy is not confined to the summit alone. The hidden highway beneath Kīlauea is real, its presence now etched into the data, waiting for the next surge to test its limits. Sulfur dioxide readings have soared past 50,000 tons per day, a level not seen since the run-up to the 2018 eruption. For the gas chemist at the Hawaiian Volcano Observatory, that number is more than a statistic. It's a direct signal that magma is actively degassing, and it's doing so closer to the surface than before. The lab's instruments break down the gas composition in real time, tracing subtle shifts in sulfur, carbon dioxide, and water vapor. The latest samples reveal a volatile, rich mix, with ratios that point to fresh magma rising into shallow rock. Each spike in sulfur dioxide matches a pulse in the summit's inflation, as if the volcano is exhaling with every surge of pressure below. But the signs aren't limited to the summit. Satellite infrared data, processed by remote sensing teams, show faint but persistent heat signatures cropping up miles from any known vent. These hotspots, scattered along the southwest rift and even further east, suggest that the hidden magma corridor is warming new ground, potentially opening pathways where none existed just months ago. The satellite's thermal eye can't see through solid rock, but it can register a few degrees of change on the surface, enough to set off alarms among scientists who remember the overlooked signals before the 2018 disaster. Adding to the puzzle, electromagnetic sensors deployed along the rift have picked up unexplained pulses, brief bursts of energy that don't match the background noise of ocean tides or electrical storms. These signals are rare and difficult to interpret. Some researchers argue they could be the fingerprint of superheated gases, forcing open new fractures deep underground. Others caution that instruments instrument glitches or natural groundwater movement could be to blame. Still, every new pulse is logged and compared against the timing of gas surges and thermal anomalies, searching for a pattern that might warn of imminent change. Together, these clues, soaring sulfur dioxide, distant heat, and mysterious electromagnetic signals, paint a picture of a conduit that is not only alive but restless. The evidence points to magma on the move, heating and fracturing rock as it nears the surface. For the chemists and geophysicists watching the data roll in, the message is unmistakable. The system is charged, and the next episode may not play out where anyone expects. Kīlauea's southern flank creeps seaward, shifting 6 to 10 centimeters each year. A network of GPS receivers, bolted to the lower slopes, captures this motion, each tiny nudge a sign of deeper forces at work. Magma pushes through the rift zone, tectonic plates stretch, and gravity tugs at the volcano's massive bulk. Beneath it all, the décollement fault acts as a hidden slipway, letting the entire southern edge inch toward the Pacific. Most days, the movement is so slight it passes unnoticed, but history offers reminders that slow creep can give way to sudden disaster. In 1975, a slip along the fault unleashed a magnitude 7.7 earthquake. The coastline lurched 3 to 8 meters closer to the sea in seconds. A tsunami followed, rising up to 12 meters and flooding villages. The scars remain, etched into the landscape and memory, a warning that gradual change can snap into chaos. The threat is not just earthquakes. Rarely, volcanoes have lost entire flanks in catastrophic collapses. Krakatau's 1883 eruption tore away 4 to 6 cubic kilometers of rock, sending it crashing into the ocean. Tsunamis topped 35 meters, sweeping away tens of thousands along Java and Sumatra. Around 1500, Fogo volcano in Cape Verde lost up to 160 cubic kilometers in a single landslide. The resulting waves soared over 200 meters, tossing boulders far above the shoreline and reshaping islands. Kīlauea's current pace is modest by comparison, but the echoes of these events are hard to dismiss. Scientists at the USGS and Pacific Tsunami Warning Center have run models simulating a large-scale flank collapse. The numbers are stark. Local run-up heights could reach 15 to 20 meters, flooding low-lying coastal communities. Yet the GPS data shows steady, not accelerating movement. No unusual spikes have appeared since the latest eruptions. The odds of a major collapse remain low, but the consequences would be severe. Civil defense agencies have responded by updating evacuation maps and scenario plans, drawing on historical cases and new geophysical models. Fresh maps now hang in community centers, marking zones at risk from earthquakes, landslides, and tsunamis. An HVO scientist sums up the tension. We're not predicting a disaster, but we have to be ready for the improbable. The mountain moves at its own pace, and sometimes it surprises us. For now, the southern flank's slow drift continues, tracked by satellites and GPS and watched by those who remember what the volcano is capable of. The risk is measured not just in data, but in the lives and landscapes that could lie in the path of a sudden cascade. In the spring of 2018, lava swept through the lower Puna district, swallowing entire neighborhoods with a force that left more than 700 families without homes. The drone footage from that eruption, rooftops vanishing beneath rivers of molten rock, roads erased in hours, still circulates in community meetings and emergency briefings. For many on Hawaii Island, the memory isn't distant history. It's the reason evacuation bags stay packed and alert radios remain switched on. Since then, the rhythm of the volcano has dictated the pace of daily life. Every new cycle of inflation and deflation sets off a wave of anxiety and preparation. Civil defense officials many of whom coordinated the 2018 evacuation, now spend evenings revising hazard maps and rehearsing response protocols. The latest maps, posted in schools and post offices, carve the island into zones, some marked in red where the lava once flowed, others newly shaded to reflect the broader area now under scrutiny. These revisions are not theoretical. They're a response to the shifting footprint of risk as ground deformation expands beyond the familiar rift zones into places untouched for generations. The tension between caution and disruption runs through every decision. Local businesses, still recovering from the economic blows of 2018, push back against park closures and trail restrictions. Farmers near the rift zone watch the data as closely as the scientists, weighing the cost of lost crops against the threat of another evacuation. In council meetings, the voices of civil defense and economic stakeholders sometimes clash, one side urging readiness at the first sign of unrest, the other warning against panic that could drive away visitors or shutter livelihoods. Yet the volcano's cycles are indifferent to debate. Each episode of swelling and release is tracked in near real time, with alerts issued when tilt meters or gas sensors cross preset thresholds. The current pattern, broad, persistent inflation, punctuated by sudden, rhythmic drops, echoes through the community as a warning. There is no guarantee where the next vent will open, only that the mountain's pulse continues. For residents who once watched lava creep up their driveways, the instrument's steady beeping is both a reassurance and a reminder. Vigilance is not optional. As scientists and officials monitor the mountain's every move, the community listens for the next sign: a tremor in the night, a spike in sulfur on the morning report, a new line on the hazard map. The rhythm of Kīlauea is now a shared experience, binding past trauma to present uncertainty. The question is not if the volcano will erupt again, but how prepared the island will be when it does. Since mid-2025, GPS and tilt meter data have recorded continuous ground inflation across Halema'u, and the southwest rift zone. Scientific imaging confirms a lateral magma conduit at 2 to 5 kilometers depth, moving up to 2 centimeters per month. Sulfur dioxide emissions now exceed 50,000 tons per day, and thermal satellite maps show hotspots far from known vents. The 2018 eruption destroyed over 700 homes, and flank movement continues at several centimeters per year. Despite these advances in monitoring and hazard mapping, key questions remain: the exact locations of future eruption sites and the triggers for major flank shifts are still unknown. Current instruments detect the volcano's inflation, deflation cycles, but not all subsurface changes are visible in real time. As of October 2025, Kīlauea's geological processes remain in flux. The evidence shows a volcano reorganizing its internal pathways, with implications for both local communities and scientific understanding. The timeline for the next major event is uncertain, but the ongoing data underscores a simple fact: Kīlauea is not stopping, and its movements demand continued vigilance.